Okay, so we're going to be learning about what is mathematical induction. Mathematical induction is basically a method for proving that a statement P of n is true for every natural number n. Again, to clarify, before we proceed, a natural number n is basically the set of numbers from 0, 1, 2, up to infinity, positive infinity. Now, some textbooks might say a natural number starts from 1, but others say it starts from 0. But for this very matter, we make our domain for natural numbers start from 0 to n of positive infinity. Okay, going back, that is that the infinitely many cases p of 0, p of 1, p of 2, p of 3, up to infinity all hold. This is done by first proving a simple case, which is also known as a base case, then also showing that we assume the claim is true for a given case, then the next case is also true. So basically how this works is like a ladder, wherein once we prove this certain step, and that when we show other steps also follow, we prove the whole statement. And this is better explicated with an example as follows. Okay, so let's start with proving that 1 plus 2 plus 4 plus 8 plus 16, with the last term being 2 raised to n, but for an arbitrary amount of numbers, is that the sum of those are equal to 2 raised to n plus 1 minus 1 for all n that's greater than or equal to 0. Let's rewrite this real quick to really show the mathematical concept behind this. So let's start with observing the pattern from these sets of numbers. Now we see that our last term is actually 2 raised to n. So this tells us something, that this should actually be a sum of 2 raised to some index I. Now if we carefully observe, 1 is actually just 2 raised to 0, 2 is just 2 raised to 1, 4 is just 2 raised to 2, 8 is just 2 raised to 3, and 16 is just 2 raised to 4, and so on for n elements. Now, we can actually write this as a summation, as a sigma notation, using this symbol, the sigma. Okay, so we start to formally write the sigma notation. We start with our lower bound, that is I equal to 0. You can use any variable, by the way. I just like to use I because it's more conventional. And then it bounds up to the upper bound of n. And for each iteration, we have 2 raised to I. So this basically means that we're adding the numbers from 2 raised to 0 up to 2 raised to n. Now we're asked to prove that this is equal to 2 raised to n plus 1 minus 1 for n that's greater than or equal to 0. For all n that's greater than or equal to 0. Now, before we start with first defining what is our propositional function. Let's say I just let p of n be the following. Now we start with a base step, because as per our definition, we should always start by proving a simple case, that is the base case, and then showing that if we assume that the claim holds for an arbitrary set of integers, then that integer plus 1 should also hold. Our base step is essentially the simplest case for our ladder, if you recall. Basically, what this means is showing that for our least element in the domain of n, we want to show that it is true. In this case, that's p of 0. So we want to show that p of 0 holds. So how do we do this? So let's start with what we're actually trying to show that holds. So it would be the propositional function p that takes an arbitrary n. In this case, our n is 0. In this case, we simply substitute our n for 0. It will become 2 raised to I. This basically just evaluates to 2 raised to 0, which essentially is just to 1. So remember, our end goal is really to show that 1 is of the form 2 raised to n plus 1 minus 1. And how do we do that? What we do basically is we expand the 1 creatively. This is where creativity in mathematics really strike and practice really takes time. So let's start with this. It's very simple. We all agree that 2 minus 1 is just 1, right? We all agree. If you want to ask, where did I get 2 minus 1? It's simply from creativity, nothing else. It's simply creativity with a goal in mind that I want to have something with 2 and 1. That's it, nothing else. There's no mathematical formula for that. Then, I want to expand 2 minus 1 such that they're still equal. Now, what if I write this as 2 raised to 1 minus 1? That's the same thing. Because 2 raised to 1 is just 2. And then 2 minus 1 is still 1. So it's okay. It's completely valid. And I can also further expand this to be 2 raised to 0 plus 1 minus 1. And voila. This is of the form this. And what does it tell us? This tells us that P of 0 holds. Now, we're done with our base step. However, this is not where we stop. By definition, again, we should show that it follows for our inductive step. That is that we assume the claim and then show that it follows for an integer k plus 1. Now, how do we go about doing that? For an inductive step, basically what we do is that we assume that P of k holds. P of k with k being any integer greater than or equal to 0. So we assume this is true and we want to show that P of k holds and implicates pk plus 1. How do we show that? Now, remember that our P of k is simply this and our P of k plus 1 is simply this. How did I get this? I simply substituted everything on the argument of P and then substituted this on the propositional function P of k, and thus I get the summation from I is equal to 0 to k plus 1 for each term 2 raised to I get 2 raised to k plus 1 minus 1. Now, we start by working our left-hand side first. Remember, P of k again is just this, and thus I just copied it here. So you don't get left out. Then, if we rewrite this sigma notation into an arithmetic form, here we get the following. 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3 up to 2 raised to k is just equal to 2 raised to k plus 1 minus 1. Now, how do I manipulate P of k such that I get P of k plus 1? This is where creativity starts. Now, I could add 2 raised to k plus 1 on both sides and the equation would still be equal. It doesn't matter. That's how we learned algebra from high school. Whatever you do on the left, you do on the right. Now, in this case, remember that this is actually what pk plus 1 means, right? And this simply can be rewritten as the summation from I is equal to 0 up to k plus 1 of 2 raised to I. Now, notice anything familiar. We can actually factor out our 2 raised to k plus 1. So this simply becomes 2 times 2 raised to k plus 1 minus 1. And from here, what we can actually do is, through the laws of exponents, remember, 2 times 2 raised to k plus 1 is simply just 2 raised to 1 times 2 raised to k plus 1. And by laws of exponents, I can just write this as 2 raised to k plus 1 and minus 1. It's crazy. And then I can further show this in the form of the original by saying that I can group k plus 1. And voila! Didn't I just show that p of k plus 1 holds because I wrote it in this form? Right? And this actually shows that p of k plus 1 holds. And then therefore, by mathematical induction, p of n true.